All right, we are going to go ahead and get started. I'd like to thank you everyone who is joining us today. Welcome to today's CNCF webinar, Resilient and Fast Persistent Container Storage Leveraging Linux Storage Functionalities. I'm Paulo Simões, Solution Engineer and Cloud Native Practice Leader at Oracle and a CNCF Ambassador. I'll be moderating today's webinar. We would like to welcome our presenters today, Philip Hasner, CEO of Qbert, Christopher Bowen-Welder, and Joel College, also from Qbert. A few housekeeping items before we get started. During the webinar, we are not able to talk as an attendee. There is a Q&A box at the bottom of your screen. Please feel free to drop your question in there and we will get to as many as we can at the end. This is an official webinar of CNCF and SL is subject of CNCF Code of Conduct. Please do not add anything to the chat or questions that would be in violation of that Code of Conduct. Basically, please be respectful of all of your fellow participants and presenters. Please also note that the recording and the slide will be posted later today to the CNCF webinar page at www.cncf.io/webinars. With that, we will hand it over to Philip to kick off today's presentation.
Thank you, Paolo, for the introduction. So my name is Philip Reisner, and I will put the Piraeus Data Store project in the spotlight today. And that is a Kubernetes packaging around LinStore. And I will begin with some slides about LinStore to give you the, let's say, theoretical background about it. And then Joel and Christoph will do live demos of the operator in action and of the STORK scheduler extension in action. Okay, so let me introduce Qbert for a minute. So we are an organization of about 30 people where our main development office is in Vienna, Austria, and we have about 10 people on the west coast of the US. And we come from an HA background and are now moving quickly into the software-defined storage area. So the foundation of all of that is the storage building blocks on the Linux kernel. So I will fly over that really quick. So there is a logic volume manager in Linux, and that's, let's say, Linux standard. It has been there for ages, and what it does is it provides you fully allocated volumes, which can span multiple physical volumes, and everything is managed through volume groups. I'm pretty sure you are familiar with that. Then that got extended with LVM thin. So in LVM thin, one of these regular LVs becomes a thin pool. And out of that, we can create thinly allocated logic volumes and also snapshots of those. And the main advantage is that the snapshot implementation in this area is a lot more capable than this one. Then there is software RAID on the Linux kernel. So everything starting from striping to mirroring, RAID 5, RAID 6, RAID 10. It has 2 different front ends. It's just one building block. Then there is 2 implementations to use SSDs as caching for rotating media, and that's missing from the slide. There's also an implementation that's targeted at using PMEM as cache for SSD, so that is called dm-write cache. On the other end of the performance scale, there's also a deduplication building block. So full-blown inline in data path deduplication. You would use that if you have, let's say, images of virtual machines where the same operating system is installed. There are targets and initiators on Linux just for iSCSI, NVMe fabrics, etc. And finally, there's also CFS on Linux, only relevant to the Ubuntu ecosystem, and it brings about the same features as the LVM stack when we look from it from a standpoint of view where we only look at block devices, not the file system itself. And then there is the DRBD technology. So the DRBD forms an important part of our data plane. So from a very high altitude, it is like a RAID 1 between a local block device and initiator. And from there it goes to a target, and that sits on top of another block device in 2 different nodes. But this is not how it's implemented. On the Linux machine itself, it will present you a block device node, so def drbd something. And the moment you open it, and the moment you mount it, it demotes the role of this drbd instance to primary, and that means everything you write there will be replicated over to the secondary. If you unmount it, it demotes the secondary, and a moment later, you can mount it here, and it will promote the primary, and the direction of replication is reversed. So the goal is to make it very easy to access it. It can handle multiple volumes in a consistent way. Since I'm a little bit time constrained, I will not explain that in all the detail. It can replicate to multiple secondaries concurrently. So this is like a 3-way replica of your data. It can also handle diskless nodes, and that can become in a cluster like in a Kubernetes cluster important when the Kubernetes scheduler decides to move around the pods, but we cannot move our data replicas as quickly, so we need a way to access it from arbitrary nodes. So you can imagine this like an iSCSI initiator that is connected to multiple targets concurrently. So for every read it needs to fulfill, it can do a load balancing scheme and send one read here and the other read there. For every write it gets down, it sends the write concurrently to both peers. Now, it also shields the application from errors, right? So if a read comes down the stack, it's sent to this node and this node fails, this server will resend the read here, get the data, and delivers it to the application. So the application is shielded from that error. If that node returns after a few minutes or hours, it will get an automatic resync, only the blocks that changed in the meantime. And when that is finished, it's reintegrated and ready for I/O again. This technology comes from an HA background and has been in development for about 20 years now. So it has a few features that only makes sense in the HA world, but it also comes with quorum. That is a feature that fits a lot better in a Kubernetes world. And what have we recently done? Recently, we optimized its metadata method in case the metadata is located on PMEM, so that we even get more performance out of it using the DOCS direct access method. Then let's come to LinStore. So far, I talked about all these storage building blocks that are in Linux. So LVM, DRBD, then there's also encryption and the caching functions and video, all these parts. And all these parts, they are compatible on the data plane, but all of them bring their own management tools. And this is exactly where LinStore comes into the picture. So the idea of LinStore is it is a distributed application that runs on a bunch of nodes, and it manages all these storage components for you and presents you one REST API, and through that REST API, you can request volumes. Like I need a two-way replicated volumes. That's the size, that's the name, etc. And on top of that REST API, we have then connectors for Kubernetes, OpenStack, and others. So let's go through that by example. So here on my slide, I call it a VM, but for the Kubernetes context, this is a container or a pod. So we have nodes that have enough memory and CPU to carry the workload, but they also have built-in storage devices. And if we get a request for a persistent volume from Kubernetes, LinStore will place two replicas somewhere. Let's assume the policy is the persistent volume should be two-way replicated. And ideally, the workload, the pod, is placed on one node where we have a replica. And this is solved by the STORK scheduler extension, and we will look at that a little bit later. So here we have the optimal layout. Each workload is co-located with one of the replicas. So that means all the read requests we have in that pod, we can fulfill them locally. We don't create any traffic on a network. Only for write operations, we need to go over the network. Now, a pod might be relocated. In that case, through the CSI-Driver, you will get a diskless DRBD resource there. So the data is immediately available. But as you see now, we also need to ship read requests over the network. And it takes either a time-triggered policy or a single LinStore command. And LinStore will allocate an additional logic volume, add that to the DRBD configuration, so it can do a resync of all the data to this new volume. And when that resync is finished, it will remove the now redundant replica, since our policy says we want to have two replicas of each persistent volume. So that's explained by example how it works. Now let's have a quick look at its architecture. So it consists of two main parts. One is the satellite. The satellite is a stateless component that needs to run on all storage nodes and all compute nodes. And in context of Kubernetes, it gets delivered as a pod, as a container, as a pod. In a traditional environment, the LinStore controller would be stateful. In the context of Kubernetes, it's also stateless, because in context of Kubernetes, we can put everything into a etcd key value store, or if you wish, you could also put everything into a SQL database outside the scope of the Kubernetes cluster. And yeah, the satellite, that's like the node agent. We use that to do the actions on the machines itself. So creating logic volumes, configuring DRBD, etc. And well, the controller is like the central part of it, and it can be relocated in case it fails. And I also need to add here that this whole control structure is outside of the data path. So that means a volume that is established continues to do I/O even if we restart the LinStore controller or we place it somewhere else, etc. Yeah, and on top of that, the controller provides our REST API, and here comes the connectors. So now let's, yeah, here a little bit too much detail for my time constraint. In the Kubernetes context, we have, well, we started with flex volume and the XRM provisioner. No one wants to use that anymore. These days, you want to use a CSI-Driver, an operator, and so on. Let's skip the other technologies in this context. Now for Kubernetes, we have packaged everything into containers, and we call that the Piraeus Data Store project. So we have the a DRBD module loader packaged as container. We have the LinSTore satellite and the LinSTore controller prepackaged. We have deployment YAML-files. We have an operator and the STORK plugin. And yeah, here is the comparison. So the Piraeus data project, everything freely available. All the source code, well, the source code of all the software is open source, but also here all the packaging is freely available. We also have a commercial offering. We call it LinBit SDS. So that's based on Red Hat's UBI containers that allows us to get a Red Hat OpenShift certification, and it comes with enterprise class support 24/7. But both versions of packaging ship you the same components. So that's the two LinSTore components, the operator, the YAML file, Helm-charts, CSI-Driver, and STORK component. Yeah, so this is then the summary. So LinStore covers you from discovering the hardware, slicing up the storage devices into the pieces we need using either LVM, LVM thin, CFS, and then it brings you the, let's say, block storage features like replication, like encryption at rest, like caching, like deduplication, and also the access and actually making it available to the node where it is needed. Okay, so this was the 20-minute version of it. And now I will hand over to Joel, and Joel will show you all that in action.
So thank you, Phil. So this is Joel speaking, and I'm also from LinBit. And I'm going to show you today how the Piraeus operator works in terms of actually installing the LinStore into Kubernetes, and also just how to actually go about using that. So I hope you can now see my terminal, and let's get going. So we're working with a pretty standard 118 Kubernetes cluster today, nothing too radical here. And it's running on CentOS 7. And otherwise, the only preparation I've done is to make sure that the thin pool module is loaded and make sure that the kernel devel headers are available so that we can compile DRBD, because that's part of the Piraeus distribution that DRBD is compiled online, as it were. So the steps I'm going to show you now are basically the steps from the Piraeus operator README. We will also post exactly this script online on our GitHub account so that you can look at exactly the steps we did. But if you just follow the README on the Piraeus operator, then you'll basically have the same effect. So we start by labeling the nodes to indicate that we want our Piraeus operator to use them. And then we continue on by preparing a bit of storage for the LinStore etcd cluster so that LinStore can store its database somewhere. And just check what that's done. So here we go, it's just created us these 3 persistent volumes ready for LinStore's database itself. So LinStore hasn't done anything at all yet, it's just preparation. So now this is the actual main step. Here we use Helm to install the Piraeus operator, and the only extra argument that we give it is to specify which kernel we're using, or which distribution, so that the kernel module loaders can appropriately prepare the kernel module. So let's see what this is actually doing. So here we see the pods that are starting, and at the bottom we see the Piraeus operator pod, which is the main one, which is controlling everything else. And this one just runs once on the whole cluster, and it's responsible for starting the other parts and managing upgrades and so on. Let's consider what happens when a user wants to create a persistent volume, or rather, when a user creates a persistent volume claim in the Kubernetes cluster, then it goes down first to this CSI, that's the container storage interface controller, that's the LinStore CSI in the Piraeus distribution. And then that CSI controller is just the glue basically that connects then to the LinStore controller, which is this one. And the LinStore controller in turn uses these etcd database to store its data, the one we just set up the storage for. And the LinStore controller has its nodes, as you just saw in Phil's presentation. These are the satellites, these node pods, and there's one for each of the nodes that we labeled so that we can provide storage. And they do things like setting up LVM, setting up DRBD, and making everything ready. And then finally, there are just these little CSI agent pods on each node as well to bind everything together at the Kubernetes level. So while that's running, we'll just consider the question of how many pods are actually involved in this whole operation. Basically, you're now seeing them all. In this configuration or this solution, there are no pods required for a resource or for a persistent volume. It's just scales with the number of nodes. So if you have some more nodes, then you'll get some more satellites and some more CSI pods. But other than that, there won't be any extra overhead of extra pods being created. And then otherwise, there's just one of the controller, one of the CSI controller, standard database, however you wish to configure it, and one of the operator. So we can see now that everything is ready and running, which is very good. So now we can consider what this looks like from LinStore's perspective. So we can contact the LinStore controller, which is running, and there happens to be a LinStore client also conveniently installed on the controller pod. So contact it there. So from LinStore's perspective, we see that there are these 4 pods which have been registered, the satellite nodes, and they're all online and ready. So far we haven't actually provided LinStore with any underlying storage devices to use, but LinStore itself will help us with configuring that, so we can ask it what devices are available. And we see here that each of the 4 nodes has got one 2 GB device available on DevSDA. So we can ask LinStore to set up LVM thin for us. So we just tell it to do LVM thin on that node. And we create a storage pool at the LinStore level, because that's the LinStore object itself. And we can do the same for a second node so that we've got enough storage pools to actually do replication. And now if we ask LinStore what the storage pools are, then we get a list here, and we see that there are these two LVM thin storage pools, which we just created, one on each node, each with the 2 gigabytes roughly available. So now we've installed and configured LinStore already. It's actually ready to be used. So let me show you how that works. Jump into a different directory. So we're going to start with a storage class, as you would expect in a Kubernetes world. So this is just storage class indicating to the CSI-Driver how to set up the DRBD replication and so on. So all it's telling us is to use this CSI provisioner, the one that is the CSI controller itself, and then to do two-way replication and to use the LVM thin storage pool. So let's apply that. And then we can use it in a persistent volume claim. So this persistent volume claim refers to exactly that storage class that we just created up here, and just tells us that it will have a storage 1 gigabyte storage volume and that it wants a file system so that it can be used from a pod that expects a file system. There's also a block mode if you want to use the block devices directly in your pods. For this demo, I'll just show the file system. So we can apply that too. And let's see what's actually happened. At the Kubernetes level, we can observe the persistent volumes, and we see that additional to the database ones we set up at the beginning, we've now also got this persistent volume created using the storage class that we specified, and that is the claim that we created. And if we look at it at the LinStore level, then we see that there are these two volumes created because it's two-way replicated. That's what we asked for in the storage class. And it's been created on each of the nodes, which are here. And finally, just to prove that it really works, I'll give a demonstration of actually using this persistent volume claim. So we're going to set up a MySQL database that's just a very standard MySQL deployment. And the only special thing about it is that the persistent volume claim is specified here and it's mounted onto the data directory where it's expected. Let's check how that's doing. So it's still loading. Okay, and now it's running. Let's actually see what that's done at a LinStore level. So at the LinStore level, we can now see that it's created this diskless volume to connect to the data, because apparently the pod was on that node. Let's just check how it's doing setting up. Yep, ready for connection. So it's certainly loaded. And since we're showing a storage system, we ought to put some actual data into it. And this just loads some dummy data into the MySQL pod. And then we just connect into that pod just to see what it's up to, see what it's done. So just grab some of the data, and then we see MySQL's running using that data. That's very general. So there you have it. And LinStore is now running in Kubernetes a very simple installation. Most of the commands I've actually been running have been diagnostic commands just to show you what's happening. The number of commands to actually install it are extremely minimal and very simple. So I hope that's useful to you all. I'm now going to hand over to Christoph, who will tell you about a different very cool feature.
All right, thank you for that demo, Joel. I'll just share my screen here. There we go, and I hope you can all see that. So, thanks for the demonstration, Joel. Obviously, that's a very cool way to get persistent or to get redundant storage in a Kubernetes cluster. It's also very easy to set up and very convenient. And that's all fine, but there's just one small problem, and Joel actually highlighted it a little bit before. Let's take a look at the pod we just created here. So this one pod, this MySQL pod that we just created, is running on node 103, right? If we now take a look at the volumes LinStore created, we can actually see that our disk full replicas, so where we're actually storing data, are on nodes 101 and 102. So the pod got started on.
Here's Philip speaking.
Yes.
Okay, I think we were not seeing what you were highlighting.
Okay.
Okay, now the screen catched up, and now we can see all the content.
Oh, so it's lagging behind, or is it working now?
Yes, now it catched up. Yes,
Perfect.
now it catched up.
Okay, thanks. So I guess I'll go a little bit slower then. So yeah, basically we can see that on the node where the pod was started, which was node 103, LinStore created a so-called diskless resource, which basically means, as Philip already explained in his presentation, it means that we're doing all the reads and all the writes over the network. So we don't have any local disk there to actually store the data on. So this is obviously a very cool feature of LinStore, and it's very useful in a lot of scenarios. But here it's a little bit of a problem, right? Because if you had, obviously most of the time the network is much slower than the disk, so this would degrade performance a lot. So let's quickly undo the deployment we did before, and we'll set it up again in a second, but only this time with some storage optimization. So this is what this STORK component is for that Philip was talking about in his presentation. And the first component we need is the STORK deployment. I'll just apply this YAML real quick and then show you what it's about, because it does take some time to set up. Right, so looking at this YAML file, it's a little bit big and intimidating, but you can actually get this from STORK. So for a basic deployment, you don't have to worry about it too much. The gist of it is that it's a three-way replicated service, and it's running the STORK command, which is again provided by the project. And we're here telling it to use LinStore as its driver. So STORK will actually be able to talk to LinStore in order to figure out where to place pods so that they get moved close to their storage. So that's what this is all about. We're also telling it here where to reach the LinStore controller, which is basically just a various operator controller pod. And let's see how it's doing. Right, seems like it started. We have our three-way replicated service here, 3 STORK instances for the cluster. Right, so that's the first piece of the puzzle. There's actually another component we have to set up, and in order to be able to use this STORK component with our scheduling. And that is the recommended way to do that is to create a new scheduler instance. And I'm just gonna do it and then show you the YAML. So here it is. Again, there's a lot in there, but this is also provided by the STORK project, so you shouldn't really have to worry about this. This is just a standard Kubernetes scheduler image. So you can see that here, it's just using the normal Kubernetes scheduler for our version. And we are giving it a name here, and that name is STORK. And we're also telling it to interface with STORK. So basically what STORK is it's an extension for the Kubernetes scheduler. So the Kubernetes scheduler will talk to STORK, and STORK will talk to LinStore. LinStore will figure out which nodes are best for the pod and give that information back so that Kubernetes can schedule the pod in the most efficient way. So again, let's see how that's doing. Perfect, it just finished setting up. Here are our 3 instances, 3 STORK scheduler instances, again, 3 were replicated. Yeah, that's part 2. Now we are actually almost done. The only thing that's left is actually telling our pod to use this scheduler. Because if we take a look at our pods again, we now actually have 2 schedulers in our cluster. One of those is the Kubernetes scheduler, standard scheduler, and the other one is the STORK scheduler. So we have 2 parallel schedulers, and we can still use the default scheduler if we would like to, but in this case, obviously, we want to use the new STORK scheduler. So in order to do that, we actually just have to edit our MySQL YAML file a little bit here. And it's actually pretty simple. It's just 1 line. Up in here in the container spec, we just have to put scheduler name and the name that we gave it, which is STORK. Save that. So now we have our new YAML file. And just so we know what to expect, let's look at the LinStore volumes again. Again, we can see here that on node 101 and 102, we have a disk for the data to be stored on. So we would expect STORK to schedule it on one of those 2 pods, right? So let's apply that again and watch what it's doing. And sure enough, it scheduled it to the node 102, which is where we have a diskless replica, a diskful replica of the data. And we can again check that. Let's look at the volumes again. Sure enough, LinStore didn't have to create a diskless replica because we have all data on disk right now. So that means that our MySQL accesses should be nice and fast because they are just going to a local disk. All right, so that just about sums up the demos. As Joel already mentioned, you can find the script for all of this on Limbit's GitHub page. And the steps that I just did, similar to Joe's, are actually documented in the LinStore's user guide. So you can read about all of this if this was a little bit too fast. It's all documented and it's pretty easy to set up. Right, thank you very much. And I think we have some time for questions.
Yeah, here's Philip. Thank you, Christoph. While I was watching the demo, I realized that Joel showed us that we use the PVCs with a file system. And I want to point out that we tested and verified that when you use the PVCs in block mode, and you can combine that with Qbert, and it also supports live migration with Qbert. And that's really cool if you manage your virtual machines within your Kubernetes cluster and also can do live migrations of such machines having persistent volumes. Okay, I think that's it from our part. And now let's hope for a few questions.
Great, thanks Philip and Tim for a great presentation. All right, and that's all the question we have time for today. I don't really was awesome. Thanks, Philip. Tim. It's a great presentation. we have more 10 minutes for, no, 15 minutes for questions. We don't have questions here, but you send on our chat your link, the link for the project. Could you show the page for the project in our for the participants, see the project, and if you have we have a page for the project. Could you share, Philip, the web page for the
okay.
link page for the project, please?
Yes.
You share on the
I will do in a second. Just
yeah,
let me open.
please.
Okay.
Oh,
Joel
great,
beat me.
great, good.
I got there first.
Yeah, great.
So this is the main page for the Piraeus project itself.
Yeah, great.
That will
The people
explain
can see right
from the highest level. And then this is the Piraeus operator, just on the GitHub Piraeus data store project. And this is the README, which is basically explaining the steps that I was showing you. And finally, here is the page that we were referencing with the files from today's demo in case you want to try it out yourself.
Great. Thank you. And there is how can communities can contribute to project?
So we're an open source project on GitHub and we welcome pull requests. And we do most of our development in the open using pull requests on GitHub. So anyone who's interested and wants to contribute code can do so that way. You can also contribute just by trying it out and seeing if it works in your environment and sending your feedback via our Slack channel, community Slack channel, or via GitHub issues. We always like to have people working on using our stuff and providing that kind of feedback.
Oh, great. There is a Slack channel for the project, right?
Yes.
Yes.
Oh, great, great. So let's check the QA. Don't have more questions. Oh, okay. Great. Thanks, Philip and Tim, for the great presentation and talking for us about your project. It's amazing. Arad, thanks for joining us today. The webinar recording in the slides will be online later today. And we are looking forward to seeing you at the future CNCF webinar. Have a great day. Take care. And thank you so much. See you.